In the mathematical field of complex analysis, contour integration is a method of evaluating certain integrals along paths in the complex plane. Contour integration is closely related to the calculus of residues, a method of complex analysis. One use for contour integrals is the evaluation of integrals along the real line that are not readily found by using only real variable methods. Contour integration methods include direct integration of a complex-valued function along a curve in the complex plane, application of the Cauchy integral formula, application of the residue theorem. One method can be used, or a combination of these methods, or various limiting processes, for the purpose of finding these integrals or sums. Curves in the complex plane. In complex analysis, a contour is a type of curve in the complex plane. In contour integration, contours provide a precise definition of the curves on which an integral may be suitably defined. A curve in the complex plane is defined as a continuous function from the closed interval of the real line to the complex plane, Z, A, B, C. This definition of a curve coincides with the intuitive notion of a curve, but includes a parametrization by a continuous function from a closed interval. This more precise definition allows us to consider what properties a curve must have for it to be useful for integration. In the following subsections we narrow down the set of curves that we can integrate to only include ones that can be built up out of a finite number of continuous curves that can be given a direction. Moreover, we will restrict the pieces from crossing over themselves, and we require that each piece have a finite continuous derivative. These requirements correspond to requiring that we consider only curves that can be traced, such as by a pen, in a sequence of even, steady strokes, which only stop to start a new piece of the curve, all without picking up the pen. Directed smooth curves. Contours are often defined in terms of directed smooth curves. These provide a precise definition of a piece of a smooth curve, of which a contour is made. A smooth curve is a curve Z, A, B, C with a non-vanishing, continuous derivative such that each point is traversed only once, with the possible exception of a curve such that the endpoints match equals Z. In the case where the endpoints match, the curve is called closed, and the function is required to be one-to-one everywhere else, and the derivative must be continuous at the identified point comes before z if x less than y. This leads to the notion of a directed smooth curve. It is most useful to consider curves independent of the specific parametrization. This can be done by considering equivalence classes of smooth curves with the same direction. A directed smooth curve can then be defined as an ordered set of points in the complex plane that is the image of some smooth curve in their natural order. Note that not all orderings of the points are the natural ordering of a smooth curve. In fact, a given smooth curve has only two such orderings. Also, a single closed curve can have any point as its endpoint, while a smooth arc has only two choices for its endpoints. Contours. Contours are the class of curves on which we define contour integration. This requires that the sequence of curves be such that the terminal point of coincides with the initial point of. This includes all directed smooth curves. Also, a single point in the complex plane is considered a contour. The symbol plus is often used to denote the piecing of curves together to form a new curve. Thus we could write a contour gamma that is made up of n contours as contour integrals. The contour integral of a complex function f. CC is a generalization of the integral for real-valued functions. For continuous functions in the complex plane, the contour integral can be defined in analogy to the line integral by first defining the integral along a directed smooth curve in terms of an integral over a real-valued parameter. A more general definition can be given in terms of partitions of the contour in analogy with the partition of an interval and the Riemann integral. In both cases, the integral over a contour is defined as the sum of the integrals over the directed smooth curves that make up the contour. For continuous functions to define the contour integral in this way, one must first consider the integral over a real variable. of a complex-valued function. Let f(R)(C) be a complex-valued function of a real variable. The real and imaginary parts of f are often denoted as u and v, respectively, so that then the integral of the complex-valued function f over the interval a, b is given by let f(C) be a continuous function on the directed smooth curve gamma. Let z(R)(C) be any parametrization of gamma that is consistent with its order. Then the integral along gamma is denoted and is given by this definition is well defined. That is, the result is independent of the parametrization chosen. In the case where the real integral on the right side does not exist, the integral along gamma is said not to exist. As a generalization of the Riemann integral, the generalization of the Riemann integral to functions of a complex variable is done in complete analogy to its definition for functions from the real numbers. The partition of a directed smooth curve gamma is defined as a finite, ordered set of points on gamma. The integral over the curve is the limit of finite sums of function values, taken at the points on the partition. In the limit that the maximum distance between any 2 points on the partition, also known as the mesh, goes to 0. Direct methods. Direct methods involve the calculation of the integral by means of methods similar to those in calculating line integrals in several variable calculus. This means that we use the following method. Parametrizing the contour. The contour is parametrized by a differentiable complex-valued function of real variables, or the contour is broken up into pieces and parametrized separately. Substitution of the parametrization into the integrand. Substituting the parametrization into the integrand transforms the integral into an integral of one real variable. Direct evaluation. The integral is evaluated in a method akin to a real variable integral. Example: a fundamental result in complex analysis is that the contour integral of z-1 is 2 pi I, where the path of the contour is taken to be the unit circle traversed counterclockwise. In the case of the unit circle, there is a direct method to evaluate the integral. In evaluating this integral, use the unit circle z equals 1 as contour, parametrized by z equals EIT, with t 0, 2 pi, then dz dt equals IEIT, and which is the value of the integral. Applications of integral theorems. Applications of integral theorems are also often used to evaluate the contour integral along a contour, which means that the real valued integral is calculated simultaneously along with calculating the contour integral. Integral theorems such as the Cauchy integral formula or residue theorem are generally used in the following method. A specific contour is chosen. The contour is chosen so that the contour follows the part of the complex plane that describes the real valued integral, and also encloses singularities of the integrand. So application of the Cauchy integral formula or residue theorem is possible. Application of the Cauchy-Gaussat theorem. The integral is reduced to only an integration around a small circle about each pole. Application of the Cauchy integral formula or residue theorem. Application of these integral formula gives us a value for the integral around the whole of the contour. Division of the contour into a contour along the real part and imaginary part. The whole of the contour can be divided into the contour that follows the part of the complex plane that describes the real valued integral as chosen before, and the integral that crosses the complex plane. The integral over the whole of the contour is the sum of the integral over each of these contours. Demonstration that the integral that crosses the complex plane plays no part in the sum. If the integral I can be shown to be 0, or if the real valued integral that is sought is improper, then if we demonstrate that the integral I as described above tends to 0, the integral along R will tend to the integral around the contour R plus I. Conclusion. If we can show the above step, then we can directly calculate r, the real-valued integral. Example: consider the integral. To evaluate this integral, we look at the complex-valued function which has singularities at I and minus I. We choose a contour that will enclose the real-valued integral. Here a semicircle with boundary diameter on the real line will be convenient. Call this contour C. There are two ways of proceeding: using the Cauchy integral formula or by the method of residues. Using the Cauchy integral formula, note that. Thus furthermore observe that since the only singularity in the contour is the one at I, then we can write which puts the function in the form for direct application of the formula. Then, by using Cauchy's integral formula, we take the first derivative in the above steps, because the pole is a second-order pole, that is taken to the second power, so we employ the first derivative of f. If it were taken to the third power, we would use the second derivative in divide by 2, etc. The case of to the first power corresponds to a zero-ordered derivative, just f itself. If we call the arc of the semicircle arc, we need to show that the integral over arc tends to 0 as or infinity, using the estimation lemma where m is an upper bound on f along the arc in L, the length of arc. Now, so using the method of residues, consider the Laurent series of f about I, the only singularity we need to consider. We then have it is clear by inspection that the residue is minus I, 4. So, by the residue theorem, we get the same result as before. Contour. Note as an aside, a question can arise whether we do not take the semicircle to include the other singularity, enclosing minus I. To have the integral along the real axis moving in the correct direction, the contour must travel clockwise, i.e., in a negative direction, reversing the sign of the integral overall. This does not affect the use of the method of residues by series. Example: Cauchy distribution. The integral resists the techniques of elementary calculus. We will evaluate it by expressing it as a limit of contour integrals along the contour C that goes along the real line from minus A to A and then counterclockwise along a semicircle centered at 0 from A to minus A. Take A to be greater than 1, so that the imaginary unit I is enclosed within the curve. The contour integral is since x is an entire function. This function has singularities only where the denominator z2 plus 1 is 0. Since z2 plus 1 equals, that happens only where z equals I or z equals minus I. Only one of those points is in the region bounded by this contour. The residue of f at z equals I is according to the residue theorem. Then, we have the contour C may be split into a straight part and a curved arc. So that and thus it can be shown that if t greater than 0 then therefore if d greater than 0 then a similar argument with an arc that winds around minus I rather than I shows that if t less than 0 then, and finally we have this. Example: trigonometric integrals. Certain substitutions can be made to integrals involving trigonometric functions. So the integral is transformed into a rational function of a complex variable, and then the above methods can be used in order to evaluate the integral. As an example, consider we seek to make a substitution of z equals EIT. Now, recall and taking C to be the unit circle, we substitute to get the singularities to be considered are at 3 minus 1/2 I, minus 3 minus 1/2 I. Let C1 be a small circle about 3 minus 1/2 I, and C2 be a small circle about minus 3 minus 1/2 I. Then we arrive at the following. Example: trigonometric integrals. The general procedure. The above method may be applied to all integrals of the type where p and q are polynomials, i.e., a rational function in trigonometric terms is being integrated. Note that the bounds of integration may as well be pi and pi, as in the previous example, or any other pair of endpoints 2 pi apart. The trick is to use the substitution where, and hence this substitution maps the interval 0, 2 pi to the unit circle. Furthermore, and so that a rational function f in z results from the substitution. and the integral becomes, which is in turn computed by summing the residues of inside the unit circle. The image at right illustrates this, for which we now compute. The first step is to recognize that the substitution yields the poles of this function are at 1 plus or minus square root 2 and minus 1 plus or minus square root 2. If these 1 plus square root 2 and minus 1 minus square root 2 are outside the unit circle, whereas 1 minus square root 2 and minus 1 plus square root 2 are inside the unit circle, the corresponding residues are both equal to minus I square root 2/16. So that the value of the integral is example. Branched cuts. Consider the real integral. We can begin by formulating the complex integral. We can use the Cauchy integral formula or residue theorem again to obtain the relevant residues. However, the important thing to note is that z1/2 equals e1/2 log, so z1/2 has a branch cut. This affects our choice of the contour C. Normally, the logarithm branch cut is defined as the negative real axis. However, this makes the calculation of the integral slightly more complicated, so we define it to be the positive real axis. Then, we use the so-called keyhole contour, which consists of a small circle about the origin of radius epsilon, say, extending to a line segment parallel and close to the positive real axis but not touching it, to an almost full circle, returning to a line segment parallel, close, and below the positive real axis in the negative sense, returning to the small circle in the middle. Note that z equals -2 and z equals -4 are inside the big circle. These are the two remaining poles, derivable by factoring the denominator of the integrand. The branch point at z equals 0 was avoided by detouring around the origin. Let gamma be the small circle of radius epsilon, gamma the larger, with radius r. Then it can be shown that the integrals over gamma and gamma both tend to 0 as epsilon 0 and r infinity, by an estimation argument above, that leaves two terms. Now since z1/2 equals L log, on the contour outside the branch cut, we have gained 2 pi in argument along gamma, so therefore, by using the residue theorem or the Cauchy integral formula, one obtains example, the square of the logarithm. This section treats a type of integral of which is an example. To calculate this integral, one uses the function and the branch of the logarithm corresponding to. We will calculate the integral of f along the keyhole contour shown at right. As it turns out, this integral is a multiple of the initial integral that we wish to calculate, and by the Cauchy residue theorem we have let r be the radius of the large circle, and r the radius of the small one. We will denote the upper line by m, and the lower line by n. As before, we take the limit when r infinity and r 0. The contributions from the two circles vanish. For example, one has the following upper bound with the ML lemma. In order to compute the contributions of m and n, we set on m and on n, with 0 less than x less than infinity, which gives example logarithms, and the residue at infinity we seek to evaluate. This requires a close study of. We will construct f so that it has a branch cut on 0, 3, shown in red in the diagram. To do this, we choose two branches of the logarithm setting, and the cut of z3/4 is therefore 1/4 is 0, 3, because f is actually continuous across. This is because when z equals -r less than 0 and we approach the cut from above, f has the value. When we approach from below, f has the value, but so that we have continuity across the cut. This is illustrated in the diagram, where the two black-oriented circles are labeled with the corresponding value of the argument of the logarithm used in z3/4 and 1/4. We will use the contour shown in green in the diagram. To do this, we must compute the value of f along the line segments just above and just below the cut. Let z equals r, where 0 are 3. Along the upper segment, we find that f has the value, and along the lower segment, it follows that the integral of along the upper segment is minus e in the limit, and along the lower segment. If we can show that the integrals along the two green circles vanish in the limit, then we also have the value of I, by the Cauchy residue theorem. Let the radius of the green circles be ρ, where ρ less than 1/1000th and ρ 0, and apply the ML inequality. For the circle CL on the left, we find similarly, for the circle CR on the right, we have now using the Cauchy residue theorem. We have where the minus sign is due to the clockwise direction around the residues. Using the branch of the logarithm from before, clearly the pole is shown in blue in the diagram. The value simplifies till we use the following formula for the residue at infinity. Substituting, we find and where we have used the fact that minus 1 equals a pi for the second branch of the logarithm. Next we apply the binomial expansion, obtaining the conclusion is that finally, it follows that the value of I is which yields integral representation. An integral representation of a function is an expression of the function involving a contour integral. Various integral representations are known for many special functions. Integral representations can be important for theoretical reasons, e.g., giving analytic continuation or functional equations, or sometimes for numerical evaluations. For example, the original definition of the Riemann zeta function via a Dirichlet series is valid only for ρ greater than 1, but, where the integration is done over the Hankel contour, is valid for all complex